Today we're going to look at Cayley's theorem, what it is, why we care, and how to prove it. Let's get started. So Cayley's theorem is a very important result from algebra, and it says that every group, every single group, acyclic, acyclic, finite, infinite, all of them, they're all isomorphic to a group of permutations. To illustrate Cayley's theorem, I'm going to use an example. The example I'm going to look at is a subgroup of the dihedral group on three elements, which remember is the symmetries of an equilateral triangle. But not only that, the dihedral group on three elements happens to also be S3, the symmetry group on three elements. And so I'm going to use the dihedral group just to illustrate how Cayley's theorem works. And so the subgroup I'm looking at from S3 is just three rotations of the equilateral triangle. I'm going to call this one R0 because I'm not doing any rotation. So here we did like one counterclockwise click. We'll call that R1. And then here maybe we did like two counterclockwise clicks, and we call that R2. Now if I did a Cayley table of this, I would get some result similar to this. And so for the identity, which is R0, composed with everything, we just get that original, the thing that we're composing with. For R1, compose R1, that's just two clicks counterclockwise, so that'd be R2. And then R1, R2, we get all the way back around to R0. And we could just keep doing this. What about R2 composed with R2? That ends up being 4 clicks around, which is back to R1. And if you notice, this is actually isomorphic to 0, 1, and 2. This is the same thing as Z3. And when I say Z3, I mean isomorphic. And that's what Cayley's theorem is saying, that Z3 is isomorphic to a subgroup of permutations. In fact, all groups are isomorphic to a subgroup of permutations. Okay, now I'm going to walk you through the proof on how to prove Cayley's theorem. And there's several parts to this. So I'm going to kind of label a sketch of what we need to do. Maybe we'll call this our strategy. So the first thing we want to do is characterize a group of permutations, or actually just a set of permutations. We'll call this S. And what we need to do is show that for any little permutation in S that we call sigma, the sigma is actually a permutation, not just something we think is a permutation, it actually is one. Secondly, we need to show that S is a group. Third, we need to map G to S with a function that we call phi, and we have to show that phi indeed is an isomorphism. So that's kind of the outline of the proof that we're about to work through. Can we do this? Yes, we can. All right, so let's get started. Okay, so first we're going to let G be a group, and then what we need to do is define what our permutation, or all my permutations are going to look like. And the way we're going to define this is we're going to call them lambda little g, and we're going to map A to GA. Now, what we mean here is we're going to define this for any little g in G. Okay, so you pick your favorite G, and then we're going to say we're going to take all the A's in the group and multiply them by G. So this is true for all A in your group. Now, the idea is maybe you have your group like this: identity, A1, A2, so on. Here's G. And lambda G is going to take all these elements and then multiply them by G. And we just keep doing that. Okay, so the claim is that this is indeed a permutation. So how do we show that? Well, what we need to show is that this is actually a one-to-one onto mapping from G to G, or in other words, a bijection. Okay, so to show that lambda G is one-to-one, we need that if I had two things get mapped to the same place once I do my permutation, that they actually came from the same element to begin with. Okay, so we're going to suppose that lambda GA equals lambda G of B. So that means our two outputs, right? When I apply lambda G to A and B, I get the same thing. But that means then, by definition, that GA equals GB. And since we have cancellation laws in groups, that means A equals B. That's one-to-one. To show onto, that means that for anything over here, for example, this guy here, that there is something over here that gets mapped down to that element. All right, so to show that, we consider A and G. Now this time A and G we're talking about on this side of the aisle. Can I map? Do I know what maps over to AG? Yes. We can say then lambda G of G inverse A, so mapping the element G inverse A, is going to be G times G inverse A, which is just A. Thus, lambda G is onto, and so it's a permutation. There we go. We got our first permutation, lambda G. And again, it looks like this. Here's G again, and I'm picking an element G, little g, and I'm mapping everything over by just multiplying everything in the group by little g. Okay, and so all it does is just scramble the elements. All right, so there's a permutation. We need a group of permutations, so I got an idea. Why don't we collect, since we did one of these for each thing in the group, why don't we collect all those permutations? So we could do like lambda G1, lambda times the identity, lambda times G2, collect all those together. And just a note, if you're following our strategy, this was kind of the part 1. Now part 2, so for part 2 of this, we need to show that we do have a group. So we're going to say, let's let G prime be all those lambda G's. Okay, so if you want to picture, like here's G, and actually I'm going to do this a bunch. Here I'm going lambda E, here I have lambda G1, lambda G2, and what I want to do is actually consider each of these mappings as an element. That's what G prime is doing. It's putting all of those together as one thing. We claim G prime is a group. Okay, now how do we show it's a group? We need to show it has an identity element. We need to show that we have inverse elements. And then maybe what's most important here is that we need to show closure. We need to show that if we compose two things together, that we don't break the system, that we don't get some sort of new permutation or something outside of this set. And we'll start with that. So to show closure, all I need to do is compose two things and then make sure that those that makes sense to us. So we're going to consider lambda G composed of lambda H of some sort of element A. All right, so we're taking A in two of these things and seeing that what do we get mapped to with this? Okay, so by definition, this means lambda G of little h times A, right? Because we're doing lambda H on A first. And then that means G times HA, right? And then since the group is associative, I can rewrite that as GH times A, which actually is the mapping of GH of A. So whatever G times H is, that's an element in the group. It has a permutation defined like this somehow, lambda GH. So lambda GH of A, where does that get mapped to? That gets mapped to lambda G composed of lambda H of A. That's actually very convenient. We actually are going to use this later. So I'm going to reference it. I'm going to put a note here of a dagger. So when I use dagger later on, we're referencing this fact that lambda GH is the same thing as lambda G times lambda H, or composition here. Okay, so we do have closure. We have an identity. The identity element is lambda E. Why is that true? Because lambda E, lambda G is the same thing as lambda G, lambda E. And that's just going to be, first you map it, just multiplying by the identity, doesn't change anything, and then you apply your permutation. So that lambda E is just mapping everything to itself. That is our identity element. This is our rotation of 0, like we did with the triangles. For inverses, you might can guess. So the inverse of lambda G is lambda G inverse. Since the same thing, if I compose lambda G and lambda G inverse, that's the same thing as lambda G inverse, which gets us back to our identity. Okay, so this is weird for us because we're treating the mappings as the elements, not the elements themselves as elements. We're treating the mappings of elements. So you got to imagine, that's why I drew this picture. here's my first element. This is the identity element in my G prime. Here's the next element in G prime. And so that itself forms a group. The third part of Cayley's theorem, though, is that so now that we have this new group, it's kind of weird. It's a group of permutations, which is what we wanted. We need to show that G, the group we started with, I think is actually isomorphic to G prime. That's the third and final part of Cayley's theorem. So how do we do that? We claim that G is isomorphic to G prime. And the isomorphism we're going to use, so if I'm trying to go from G over to G prime, what's the isomorphism I want to use here? I think what I'd like to do is take element G and map it over to the permutation that depended on G, lambda G. And that's exactly right. That's exactly what we want to do. We're going to say we have an isomorphism going from G to G bar, or we have this function phi going from G to G bar, where phi of G, so I'm taking an element in G and I'm mapping it to a permutation in G prime called lambda G. All right, so keep up with this. That means that we're taking an element G and mapping it to a function lambda G. Okay. Now, how do we show that this is an isomorphism? It's got to 1, preserve operations. 2, it has to be 1-to-1. And 3, it needs to be onto. I'm going to say clearly operations are preserved, since by my dagger earlier we had that phi of GH equals lambda GH. That's lambda G, lambda H. See, that's what we showed with dagger earlier, which is the same thing as phi G, phi H. That's the isomorphism property that we need. We say the operations are preserved. Okay, so that's a big deal. The last things that we need to show is 1-to-1 and onto. Those are not extremely difficult, just like we did earlier with lambda. All right, so we're going to say if phi of G of A equals phi of H of A. Now wait, what does that mean? Remember, phi of G is getting mapped to lambda G. So this is lambda G applied to element A from the original group. And that equals lambda H of the element of the original group as well. So again, that means lambda G of A equals lambda H of A, which we know means GA equals HA. And so that implies that G equals H. This is how you show 1-to-1, that if you start with two same outputs, you end up with the same input. All right, so to show onto, we'll throw out clearly again, a dangerous word, but I think we're safe here. Clearly phi is onto, because if I take any output, remember the outputs are the permutation, can I get an input that maps over to it? Yes, that is phi of little g, and that's true for any g and g. I mean, that's how we just defined it. And thus, Cayley's theorem is proven. We have shown that any group G can be written or is isomorphic to a group of permutations. End of proof, and we feel very happy about that. Okay, if you're not used to kind of longer proofs in mathematics, maybe this is a good example to start with. What you want to do is kind of mentally compartmentalize the chapters of this proof. We had 3 big chapters of this proof. So if you break it up into little chunks, it gets a little easier to wade through the progression of things. But keep going over it. My advice in mathematics is when you feel like you're starting to get just lost in a sea of symbols, that's when you need to stop. Don't try to slog through it. Stop and just backtrack a little bit. Try to make sure that those symbols maintain their meaning. Otherwise, we feel like we're just kind of regurgitating a bunch of nonsense. All right, guys, if you have questions, please let me know. Leave a comment, send me an email. I'd be happy to help. Thanks for watching, and I'll see you next time. Take care.